Thank you, Giacomo. Yeah, so what even is quantum anyway? Yeah, so who am I and why am I here? These are the kind of existential questions that I guess you find yourself asking if you've been working in quantum for too long. But yeah, I'm Max. I actually did my PhD with Tim Freegard. So my doctorate was basically a 4-year long version of his tutorial from Sunday. And since then, I've been working in industry. I've worked with Q Control, where I worked on atom interferometric inertial sensors, specifically to measure gravity. And I work now for Aquark Technologies, where I've been building atomic clocks. And by the end of this talk, I'm kind of hoping that I might convince you that these two things are essentially the same thing, and they're not really all that quantum at all. So yeah, Giacomo and Joan kind of kindly invited me to provide, I guess, some sort of pre-dinner entertainment. So now we're all a little lubricated, I thought I'd decide to kind of embrace the spirit of that and have a bit of fun. So I'll maybe say some things that I wouldn't say in a more formal setting. I don't think I'm going to say anything that's wrong in spirit, but I would certainly kind of welcome debate and questions and all that over dinner. So on that basis, outline is really simple. I'd like to play a game, and the name of the game is It Quantum? So we're going to come up with a list of quantum-sounding things and then decide how quantum they really are. So before we start, I guess I'd like a show of hands. How many people here feel like they've either worked in or with quantum technologies before now? Okay, so I think maybe it might be more of you than you think, but let's continue. What comes to mind when you hear the word quantum? There's a blank slide here. We'll fill it in together. Anything from anyone in the room, what do they think would come to mind when they hear the word quantum? So I'm going to start. I work in quantum, so Heisenberg's uncertainty principle is something I think of. Anyone want to put their hand up, say something that sounds quantum, and then Giacomo's going to write something on the board? Yes. Spin, spin, spin. That's a good one. Giacomo, can you write something on the board? Keep them coming. Okay, we've got spin, we've got entanglement. Cats. Cats, yes. What was that one, sorry? Oh, okay, yes. Bras and cats, yes. Identical particles. Any more to come from the room? Charge. Okay. Quantization of charge. Atoms. I like that. Wave-particle duality. Giacomo is doing an awesome job of writing very fast. States. States. Discrete states. uh, let's not get political. Okay, yeah, so let's leave it at that. You have done your job. Thank you so much, Giacomo. So yeah, I prepared a list of my own. I work in quantum technology, but don't actually want to leave things up to chance. But it's interesting to see what kind of overlap we've got here, right? So entanglement came up on both. The one I expected to come up that didn't on this list was superposition. That's something I tend to think of as quantum as well. Cats definitely came up. Particles, atoms, wave-particle duality, we're kind of looking at matter and particles all being this kind of wave thing. States, that comes up as kind of discrete states that kind of would be the quanta in quantum. And I threw in atomic clocks and matter wave interferometry at the bottom there as well, because I work in atomic clocks and matter wave interferometry, so I thought I should probably include what I actually work on in this talk. Okay, so let's start debunking some of this stuff. Heisenberg's uncertainty principle. Well, you guys know an uncertainty principle already, right? You know about time and frequency, and you know that if you have an oscillating signal in time, if it's truly monotonic, then it doesn't start or end in time. And if that signal is of finite duration, then it's going to have a spread in frequency content. And in general, the shorter that pulse, or the more certain I am of its arrival time, the broader the frequency spectrum, or the less certain I am of its frequency. So that's true of wibbly wobbly things in time. I can have wibbly wobbly things in space as well. I just change some axis labels and replace the temporal frequency omega with a spatial frequency k. And I can have waves that travel through space if I have both a temporal frequency and a spatial frequency, then I have a wave which will propagate with a velocity which is given by the ratio of those two frequencies. And this is basically our picture of light right up until the turn of the 20th century, when evidence seemed to arrive that this wavy thing, light, seemed to be arriving in little packets of energy, and those little packets of energy would actually be proportional to the frequency of the light with this suspicious-looking proportionality constant here. And for lack of a better word, we started thinking, well, maybe these things are kind of particles of light. Okay, that's a bit weird. So then this guy De Broglie comes along, and he says, well, maybe we've got things backwards, and I'm refraining from using my French accent very hard. This wavy thing that we call light seems to have particulate bits to it. Maybe everything we think of as particles is just waves. And he posited that every particle is actually a little wave packet whose spatial frequency is proportional to its momentum. And the proportionality constant would be the same as the one that relates its energy to its angular frequency. And this all seems like a bit of a leap. But I mean, he proposed it based on relativistic arguments. And if it all stems from Einstein, then it must be true. So, okay, sure, we'll take De Broglie at his word. And Heisenberg's uncertainty principle is just Fourier theory applied to these De Broglie waves that he's posited. So if I have a particle and it's localized in space, which fits with my experience of particles, then it must be composed of a range of spatial frequencies. And De Broglie would say that that would mean that they have a spread in momentum. Now, the corollary to that would be that if I have a particle with a very well-defined momentum, then it must be spread out in space. And in general, the product of this spread in momentum and spread in position must be greater than or equal to some finite value, which is just given by this proportionality constant. And that's just bog standard Fourier theory applied to these weird waves that De Broglie has posited. But Heisenberg's uncertainty principle, just Fourier analysis, nothing quantum going on there. So I'm going to assign it a 1 out of 10 on the quantumness scale. It does, though, require us to accept De Broglie's premise that particulate matter is actually waves, which, yeah, is a bit weird. I am going to nerd out and go on a sidebar here. For a free particle, its energy is basically dominated by its kinetic energy, which goes as the square of its momentum. But we have these two kind of equations which are relating the spatial frequency to the momentum and the temporal frequency to energy. And kinetic energy goes as the square of the momentum, so we've got a quadratic dispersion relationship. It looks like these matter waves are propagating in a nonlinear medium. And this is all a bit out there, but it's stuff that I understand. I understand waves, I understand dispersion, and who's to say that the universe isn't just wavy in its fundamental nature? So it doesn't sound too outlandish to me. You might disagree, but it's my talk, so I'm going to give this matter wave thing 3 out of 10 on the quantumness scale. But the cool thing is we can do the experiment to verify it. We know how to play with waves. We can do diffraction experiments. So, the canonical doublet statistics experiment, right? I've got a plane wave incident on 2 slits, and wave fronts from one slit will interfere with wave fronts from the other slit, and we get bands of constructive and destructive interference. And if this is a light wave, if I were to stick a screen here, I can see this represented as light and dark interference fringes. There's nothing quantum about that. And there seems to be this trend lately of otherwise good science communicators doing diffraction experiments with lasers and claiming that they've proven something about the quantum nature of the universe and how light's taking all paths at the same time, and it's all really spooky. And it's just basic optics. They're not doing anything that would have surprised Huygens or Newton or anyone kind of post-Enlightenment. It's just situation normal to them. I mean, they might be kind of surprised by the wavy light one thing that you're doing to do the experiments, but the diffraction part of the experiment they will be completely happy with. Okay, so that's for light beams. Well, what if I do the same thing with an electron beam, like in one of those old oscilloscopes? Turns out I see the same diffraction pattern. So, I mean, De Broglie was right. Matter is waves. and we just have to deal with it, and it's not that weird. Except I probably need to pick a side here, right? Is it particles or is it waves? I've been talking about kind of both of them. If I were to reduce the intensity of that wave all the way down so I don't see anything on the screen, I can make that screen persistent and expose it for a really long time. And I'd expect to see this interference pattern build back up. Just expose it for a long time, I've got a really weak intensity light, I would see the interference pattern come up. And that is what I see, except that the interference fringes seems to build up and the waves seem to be arriving on the screen in little localized packets of energy again, much like we'd imagine as if it was a particle. And these packets fall more favorably at the points of constructive interference, and they don't arrive where there's destructive interference. It's like perhaps the intensity of this wave is determining the probability distribution for where the individual packets of energy of the wave could show up. And that's the same whether this wave is light or it's matter. And is that weird? Well, is this weird? See, I haven't seen one of these before. This is a Galton board, and there's a probability distribution here for where the balls will end up when they reach the bottom of it. But we only see that probability distribution build up after we drop many balls through this experiment, and they probabilistically land where they should end up. So we have a series of pegs. Each time a ball hits a peg, there's a 50-50 probability of it going left or right. And we have a cascade of these pegs, and so at the very bottom, there's a very small chance that the balls will reach the outer extremes. Mostly they accumulate in the middle. It's a binomial distribution. So we have an underlying probability distribution, like our diffraction pattern set by the pegs, that's only revealed by dropping many balls or particles. So yeah, wave-particle duality, 4 out of 10. It's not that weird. Except I can be happy with the concept that particles are wave packets, right? And I can get an intuition for probability distributions, that's okay. But this probability distribution isn't some global property. It is the particle. And in order for one particle wave packet to diffract through both of these slits, it has to be bigger than the slit separation. And then it will splodge out in a diffraction pattern. But I don't see splodged out particles. They're spatially localized once they hit the screen. So before they hit a screen, the particle is this. But then once it hits the screen, it is this, or it is this, or it is this. If I were to task a PhD student in my quantum lab to spend their day watching a point on the screen, waiting for flashes, and then another one to do the same for another point on the screen, then as the particle goes through the apparatus, there's an equal or roughly equal probability that either student will see it. But then if one does, there's zero chance that the other will. It's like this macroscopically large, wavy thing collapses to a single point as soon as we look at it. And that's spooky action at a distance. That was Einstein's big problem with quantum mechanics, and it's just weird. That's quantum. We can't explain it. Like, I'm not going to lie, 9 out of 10 quantum. Yeah, this is strange. So some of you who have heard popular science talking about quantum will be thinking, well, I thought spooky action at a distance was all about entanglement, and you might have heard about particles with correlated spins traveling in opposite directions towards maybe Alice or Bob, and now when Alice measures her particle spin, then it does something to the spin of Bob's particle or some such. And I mean, that's just a version of the same thing. It's just a wave function that's spread through space and time that describes probabilistic outcomes, but now for multiple particles. And why should that be any weirder than for one particle? So I described this experiment with light and with electrons, but we can, and we usually do, perform this type of experiment with atoms that are comprised of multiple particles. So take a hydrogen atom. If I throw one of these at these slits, then it's described by kind of one splodgy thing, and the splodgy thing says that there's some probability that I'll find a proton and an electron together here, and maybe there's a slightly stronger probability that I'll find a proton and an electron together here, and there's negligible probability that I'll find a proton here and an electron here. They're highly spatially correlated. They are entangled. The weird thing isn't that the spodgy thing can describe multiple particles, like 3 out of 10 entanglement. The weird thing is how the spodgy thing stops being a spodgy thing. And if you can answer that, then you'll get a Nobel Prize. But we're not here to win Nobel Prizes. We're here to build inertial sensors. So let's move on to less weird stuff. Like cats. Cats aren't quantum. As somebody who owns a cat who enjoys sticking its head in boxes, I don't want there to be poison in that box. So the whole Schrodinger's cat thing about the box and the cat and the poison, don't do that experiment. I'm not going to entertain that one with a rating at all. Discretization. So where do these little packets of light energy come from? Well, we call them photons. And are they weird? Well, it's emitted from atoms that have these discrete energy levels. And okay, here's a breakdown of how light interacts with atoms. Atoms are lazy. They like being their lowest energy level. If a photon comes along with just the right amount of energy to excite the atom up to a higher energy level, then it will. The atom will gobble up the packet of photon light energy and store it as electronic energy in its little atomic belly. That's what we call absorption. But the atom can't hold onto that electric energy for long, and after a while it'll burp it out of the photon traveling some random direction. That's what we call spontaneous emission. Incidentally, like how long an atom will, on average, keep that electronic energy in its belly is inversely proportional to the range of frequencies that that emitted photon could have. So atoms with very strong stomachs make for very good optical frequency standards. But anyway, if all this light that we see comes from a finite number of atoms burping out little packets of photon energy, then the fact that light should arrive in little packets of photon energy doesn't seem all that surprising. That was the view of me when I was naive in my undergraduate days, and if I'd thought a bit deeper, maybe I'd have been more troubled. But for the purposes of this talk, you might have guessed I'm being willfully naive. So the fact that photons exist, 1 out of 10 for quantumness, by which I mean weirdness. But then there's this third process. When a photon arrives at an atom and it's just the right frequency for the atom to gobble it up, but the atom's already full. And in that case, the photon passes straight through unimpeded, but the atom emits another photon in exactly the same direction with exactly the same frequency and phase. That's stimulated emission, and that's some weird quantum shenanigans that I can't explain. That's 7 out of 10 on the weirdness scale. And it's this that gives us lasers. So if I want to make a laser, what do? I take a bunch of these atoms with their discrete energy levels, and I stick them in an optical cavity. So these are mirrors here. And I pump in some energy into this system, and the atoms go up into their excited states. And at some point, one of these atoms is going to burp out a photon, and then that photon is going to hit another atom, and this stimulated emission thing is going to go on, and that one photon will become a couple of photons, and then those 2 photons will go and hit more atoms, and then they'll bounce around on the mirrors a bit, and we'll get lots and lots of photons bouncing around in this cavity, creating more and more photons, and eventually, many of those photons will leak out of the mirrors, and I have my laser. Stimulated emission, weird. Lasers, weird. 7 out of 10 on the quantumness scale. And that's 1960s technology. Okay, so I was talking about atoms with discrete energy levels. What's with the discrete energy levels? Well, we're engineers. Everything is just a simple harmonic oscillator, right? And we can accept mechanical systems having discrete eigenmodes of oscillation. So here's a 2-level system. It's just a couple of masses on springs with a spring constant k, coupled together by a spring with a much weaker spring constant, kappa. And the normal modes are pretty intuitive here. These masses can oscillate in phase, like this. And in this case, the middle spring is doing no work because it's always the same length. So the frequency here is just the one given by the square root of the common spring constant K over the common mass M. That's this mode here. Otherwise, they can oscillate out of phase. And in that case, the spring is expanding and contracting in the middle and contributing to the restoring force. So this mode has a higher frequency that's the combination of both spring constants. Fine. Now here's the cool thing. So Frimmer and Novotny said, we can drive this system by modulating the springiness of these two big springs by an amount delta K. So I keep the total springiness the same, but as I make this spring on the left weaker, I make this spring on the right stronger, and vice versa. And I do this at a frequency which is equal to the difference between the frequencies of the two modes. Okay, so I set up the masses oscillating in one of the fundamental modes, and it turns out when I apply this modulation, I drive the system into the opposite mode and back again at a rate that we call the Rabi frequency, which is proportional to the amplitude of the modulation that I'm applying to the springiness of the springs. Now, this only really makes sense if the modulation amplitude is low enough that this Rabi frequency is much lower than the frequency splitting. But in that case, the peak displacement of the masses here remains constant through this cycle. But there's more energy in the system in this mode because the central spring is doing work than here, where it isn't. So we have an energy which is proportional to the frequency at which the system is oscillating. And we have these discrete energy levels. And in one half of the cycle, the modulation is doing positive work, and in the other half of the cycle, it's doing negative work. We're basically adding and removing energy from the system with little springy photons. So yeah, atoms are just masses on springs. There can't be anything quantum about discrete energy levels if we can realize them classically. Oh yeah, that was me outlining Rabi frequency. That was me giving it a 1 out of 10 rating. Okay. So if I were to look at this, one of these masses on the spring, and watch it oscillating, and I took the Fourier transform of that oscillation, I could distinguish by seeing the peaks in the frequency spectrum which mode the system is in. So if it's in the lower energy mode, I'll see a peak at the lower frequency. If it's in the higher energy mode, I'll see a peak in the higher frequency. As I'm driving it between these extremes, I'll see peaks at both frequencies. The system will be in a superposition. Superposition, not quantum. Anyway, yeah. If I stop the modulation after a quarter cycle and watch one of the masses, and I see the amplitude of its oscillation increasing and decreasing at the beat frequency between the two modes. But the beat frequency is the same as the frequency I'm driving the system at. That's the Rabi frequency. That's the modulation frequency. I chose that to be equal to the beat frequency. Therefore, they are in phase with each other. They're phase synchronized. So I can stop the drive, wait for some duration t, and then re-engage the drive for another quarter cycle to complete the transfer to the opposite mode. That might sound weird. I think I've got a video of it here. So a couple of masses on springs. I've started them in one of these fundamental modes. And I'm going to click this button here, and this turns on this modulation where I'm increasing the springiness of one spring, reducing the springiness of the other, at this frequency, which is equal to the difference in the frequency of the two fundamental modes. I stop it here in the middle, where it's in the superposition. And I see the system beating at that frequency, which is equal to the difference in the frequency between the two fundamental modes. And I can leave that going for as long as I like, but I can re-engage the modulation at any point I choose, like maybe now, and continue to transfer the system back into the opposite mode. Cool, there it is. Here's a schematic of that modulation. So we drive for a quarter of this, what we would call a Rabi cycle, and stop for a period t, and then continue to modulate into the other mode. That's just a schematic of what I just showed with the video. Okay, but what if we drive with a frequency which isn't exactly equal to the beat frequency? Well, now they'll drift out of phase in this kind of period t, and when I start the modulation again, it will be maybe in phase or out of phase with the beat. And so the mode in which the system will end up will change based on the phase difference between the modulation frequency and the beat frequency. So if we plotted the energy in one of these modes after this pulse sequence as a function of the drive frequency, then we would expect the perfect transfer into the high energy mode when we drive with a frequency which is equal to the beat frequency. And then we see fringes where the modulation and the beat frequency are in or out of phase after what we call the interrogation period T. The spacing of the fringes will be inversely proportional to the interrogation period. So if I make it really long, then I can measure the beat frequency really precisely. This is called a Ramsey interferometer. Now, obviously, there's a finite bandwidth, so these fringes are kind of superimposed on this resonance pedestal here. But yeah, that's the basis of an atomic clock, except it's classical. So it can't be quantum, 1 out of 10. Now, you might be saying that was a fun toy model you put together in Python, but I mean, you can't really make an atomic clock with masses on springs, right? Well, no, not masses on springs, but this is the classical system. So this is a nanomechanical oscillator. It's got two modes of oscillation, in plane and out of plane. They have slightly different frequencies, and you can drive it with these electrodes here. And this group here demonstrated coherent control of this nanomechanical oscillator between these two modes and demonstrated Ramsey fringes. They've made a classical atomic clock. Few notes to wrap up. If I made this thing in real life, then there'd be some damping, right? And there'd be a characteristic time constant, gamma, associated with that damping, and that would affect my ability to resolve these peaks in frequency space, and also limit how long I could do the interrogation for. Turns out, there's not much friction going on in an atom, so this damping is really small. Atoms are really high Q oscillators. Now, they're subject to this issue that we can't really measure the superposition state. Like spooky action comes and bites us again, so that we only ever probabilistically see the atom in one or other of these modes, with the probability weighting given by the superposition. But nature has given us abundance of these atoms, and the manufacturing tolerances are great. So if I tried to make multiple versions of this mass spring system, I mean, you guys know better than me that tuning the frequency of all of them to be the same would be a nightmare. But my atoms are all the same, and I can perform this clock sequence on millions of them at once. So statistics are on my side. I can measure the fraction of atoms I find in each mode and essentially think of it as a continuous variable describing the distribution of the energy in the superposition. Now, in general, the uncertainty scales as 1 over root n, my capacity to resolve that superposition. Quantum weirdness, again, actually lets me do better than this. Like, if all the atoms are, If all the atoms are entangled, then there's a single spotty thing that describes them. I can basically get this down to 1 over root n by taking advantage of entanglement. But entangling a lot of atoms is really hard. So my 10 million atoms that I could generally use to measure this 1 over root n turns out to be a few thousand atoms when I get to the level where I have 1 over n scaling. And I'm probably better off investing that time and effort in just getting more atoms. So yeah, is it an interesting engineering problem to make metrologically good use of this quantum weirdness thing that we call entanglement? Yes. But in the short term, just have more atoms. I said I'd talk a little bit about matter wave interferometry. I've got about a minute left. I can do it quickly. Basically, it's the same thing, except now my atoms are in an optical standing wave with the wavelength of a few hundred nanometers, and where the atom is in that wave affects the phase of this modulation here. So now I can do this Ramsey sequence again, and instead of saying how much my atom has drifted in frequency, it's telling me how much my atom has moved in this wave. So I can do a measurement. I can say, OK, it's moved this much modulo one wavelength. I can do another sequence, and I can say, after that, it's moved this much. And if there's a difference in how much it's moved each time, then I've got an acceleration. So I've got an accelerometer. Except what am I actually measuring here? I'm measuring how far an atom has moved in a given time, and it's moving along this wavefront. It's a frequency, because it's a phase that's changing in time, and I'm measuring a change in, if I think about it, I'm just dropping clocks. So I'm doing the same thing. And those clocks might as well be mechanical, but then they'd have a load of drag and air resistance and stuff. Matter wave interferometry is a bit more weird because I've got a spatial superposition, and that does factor into it. But really, I'm just dropping clocks. Okay, wrapping up. Yeah, quantum does get weird. Spooky action at a distance is really weird. But I think the take-home message here is that we can use the fact that nature has given us an abundance of identical atoms to basically average out all this quantum weirdness. And for the quantum tech that we're actually using, with the exception of the laser, which is really weird, we can just think of atoms as very high Q factor oscillators with excellent manufacturing tolerances. Now, coincidentally, Aquark technologies are using MEMS techniques to miniaturize cold atom technologies and make them more accessible. So if I've convinced you that maybe quantum is something you want to come and play with, if you like high Q oscillators, come and talk to us. And thanks. I know I've left basically no time for questions, but yeah, if there's time, I'm happy to take a few. Otherwise, yeah, come talk to me over dinner and we can maybe talk about quantum and yeah, have some fun. Thank you.